presentation, the breakout session, and we would just wait for all the other participants to join in and catch on. But for all of you participants who have joined until now, we are also having this session recorded live. So you will have the recordings on YouTube, and we will share the link. But do not forget to ping all of your friends, team members, colleagues to join us as soon as possible. So with that, I would introduce our speaker for the breakout session. You must have seen him in the mentor session, mentor channel. He's one of our esteemed mentors, Mr. Andrei, and he's going to take you through the key features of Pravega. So welcome, Andrei, and thank you so much for taking out time to do this session for us. Over to you.
Hi, everyone. Good morning, good afternoon, good evening, depending where you are. I'm Andrei, and I'm one of the original developers and founders of Pravega. So along with Shrikant, who spoke earlier today, and Tom, who will give the other breakout session tomorrow, we are the three founding members of this project. I am very happy that we're having this hackathon, and I'm very excited to see what you guys will end up doing the next couple of days. So, in this first breakout session, I will give you a overview of features of Pravega. So I will not go into too many details for any of them because I do not have enough time. But this should give you a good introduction about each of them, and then you can go and follow up on the documentation on Pravega.io. I have a link to that at the end, and you should at least know of their existence, so you can go and follow up with examples and other more in-depth readings. So that being said, let's begin. So we'll talk about a little bit about 6 major things. What is a segment? How do we make streams from segments? How do transactions work? I'll talk a little bit about state synchronizer, but just a little bit because I'll leave the rest to Tom to talk about it tomorrow. But if you like a heads up, this should be a good intro. And last but not least, I'll talk about the latest thing we're adding to Pravega, which is still under works, which is key value tables. So let's begin with segment 101. So segments are the fundamental primitive enabling everything else to work in Pravega. Pretty much everything else you see in there: streams, key value tables, state synchronizer, and schema registry, anything you think about, everything is based on the segments. So segments are not exposed directly to the outside, but in order to understand how Pravega works, it's important to understand what everything relies on. So let's talk a little bit about segments. So at its very essence, a segment is nothing else but an append-only sequence of bytes. You append at one end, at the tail, and you can read either from the head or you can read arbitrary positions. The key thing here is append only, which means you can only append, but once you append, the data becomes immutable, so you can never ever change it. And that is a very important thing in Pravega. Another key thing is, you may have heard this from Flavio earlier today, writes are durably persisted before we act them. So as opposed from other messaging systems out there, we never acknowledge a write until we have durably persisted it and replicated onto some media. So that means even if we crash, we are not going to lose your data. That's actually one of our key driving principles. Another thing to consider is that a segment at any given time is owned by a single segment store. So even though a stream is distributed across the entire cluster, a segment at any given time can only be processed by a single segment store. So all of the requests that relate to that guy, whether they are appends, reads, or whatever you want to do with it, they are routed to a single segment store. That simplifies a few things and enables us to provide the consistency that we want to provide. All right, let's give a quick overview of what the operations on a segment can be. Okay, most important one, append, because without appending, we cannot do anything to a segment. An append writes an atomic sequence of bytes at the tail of the segment. the word atomic is important because, hey, suppose you get an event from the client, that event is not going to be interleaved with any other events from any other writers or even from your own writers. So if you give us a block of 100 bytes, that block would be in there contiguously in the segment. So it's not going to be broken down. An important thing that we can do is we can append at the end of the segment, but we also have something called offset conditional appends, which means only append if the kernel length of the segment matches whatever value you provide us. Also known as the single writer pattern, this enables higher level functions to work properly. And one of those is the state synchronizer. I'll talk about it in a few slides. Of course, a segment would not be useful unless you can actually read data from it. So, but as opposed to appending, reading, you can read bytes from any arbitrary offset. You don't have to read just from the beginning or just from the end. Give us an offset and you can read the data from there without any problems. Another interesting thing is that you may not need, you are not constrained to reading just data that has been written. You can also read data that will arrive in the future. Well, you may wonder, okay, how is this possible or useful? So suppose you want to know, okay, you have consumed all the data within your segment. You've read all of the bytes within it, but you want to be notified right away as soon as new data gets appended assembled by a writer. So what you do is you can register a read at the end of the segment, which is also known as a tail read, and you will be notified when new data arrives for that segment, and you also get the data. So that will help you from having to do a pull loop or a busy wait loop for you to continuously check for your data, and the Pravega will just notify you how it works. Again, this is not something you're going to have to write because this is already baked in and used by our client via the Stream API. Okay, in order to perform retention, when you write to a stream, you always append to one, but you only have so much capacity in your data center to store data. So eventually you want to do some retention. The way you do retention from a stream, you have to cut from the beginning. You can delete segments, but every now and then you want to go and do retention somewhere in the middle of a segment. Well, in order for that to happen, one useful feature for segments is that you can do truncation from the beginning. So don't confuse this with other file systems like the regular file system or HDFS, where you can truncate from the end, when you just delete that part from the end. In our case, you delete from the beginning, which is why we call this head truncate. An important thing here is that if you delete from the beginning, the remaining offsets will stay fixed in place. So if you have 100 bytes in your segment and you delete the first 50 bytes, the remaining 50 bytes will begin at offset 50 to offset 99, so they will not shift down. We decided to do that because we want to maintain consistency. If you have moved, if you have shifted the bytes downward, then the data that you have written to your segment may have changed from the point of view of a writer. We don't want that. And the last operation that we want to talk about is sealing. When you seal a segment, after the operation is done, no further modifications can be made to that segment. You may no longer append, you may no longer modify its properties. The only exception is you can still truncate from the segment. All right. Let me talk a little bit more about something called segment attributes. Segment attributes is our custom metadata for segments. Of course, every segment has something like length, start, offset, which is where you truncate, and some other properties which are used internally. However, you as a user may want to set some custom metadata for our segments, which is particular to the data within that segment. And we enable this via something called segment attributes. Traditionally, because we only used it for client writer IDs, I'll talk about it in a bit. The metadata is pretty much 16-byte keys to 8-byte values, and you'll be surprised how much stuff you can do with this small constraint. I'll give you some examples in a bit. One of the reasons why we chose them to be fixed size and so small is because we need to support literally hundreds of millions of such entries per segment if possible. While you in your real life or in the hackathon examples, you may not even get close to like 1,000. There are use cases out there where we actually have to store that many attributes. And having them be small like this helps a lot. How do we store these things? Well, we designed our own B+3 index, append only B+3 index on our tier 2 long-term storage, and we put 2 layers of caching over it. So our long-term storage is also an append-only media, and our B3 is designed for those constraints. And it doesn't have that many problems that usually you get with B3s on append-only media, like red amplification. We solved many of those problems. Very interesting. So what do you do with these attributes? So you can update them normally. You can say, okay, I want to set this attribute to this value or whatever. But that doesn't give you too much flexibility. One thing which is very, very useful is atomic conditional updates, also known as compare and set. You allow the updates only if the existing value which is stored on the server matches whatever you give it via the client. So if you have attribute A and it has value 1, you say, okay, update A to value number 2 only if the current value is 1, then it's going to go. But if you say update to 3 only if value is 2, then that update is going to be rejected and because the value doesn't match. On its own, such a conditional update doesn't make much sense, but we can combine this with segment appends. So when you append some data, some event to the segment, you can say, okay, append this segment and update this attribute if and only if the value of this attribute matches whatever it is right there. I'll tell you in a bit how this is useful. Another thing you can do is basic arithmetic. So you can go and increment, add, or subtract values from an attribute. And we do this to keep track of various metrics for segments, which are useful for our scaling process. Okay, well, I just mentioned use cases. So what do we use this for? So we have some core segment metadata, internal uses, and some of this is segment metrics. How many events do we have in there? How many different writers do we have, and so on. And this is good for all scaling purposes. We have about 20 hard-coded attributes used for various reasons. But from a client point of view, which is the reason why we built these attributes in the first place, is we store all the writer IDs and positions. So each event stream writer has a unique ID which generates internally, or it has a way to retrieve it if it has to recover. And every time it makes a write to the server, it conditions that write on its internal event sequence number or the position to match whatever it thinks was on the server previously. So that means in case of a network disconnect or timeout or crash on the server, on the client, or whatever reason, when it eventually reconnects, it knows exactly where it left off. So it doesn't resend a previously sent event twice, also known as duplication, or misses events, in which case it loses data. So this is the foundation that we have for our exactly one semantics on the writer side. So it's very important. That's why we have it in there. I'll tell you at the end, we also use them for a different purpose, but I'm not gonna tell you right now because I'll save it for later. Okay, so the core thing for Pravega is that it's a streaming storage. So the fundamental primitive that we expose externally from Pravega is called a stream. Flavio already told you about streams, and that streams are made of segments. But now I'll tell you how these segments are composed to create a durable, elastic, and virtually unbounded stream. I say virtually unbounded because it is limited by the capacity of your cluster or data storage. I mean, of course, if you don't have enough storage capacity, there's only so much you can store in there. But there. So A stream is a foundation for a reliable streaming system. It's a high-performance, durable, elastic, infinite log with strict ordering and consistencies. That's a lot of words we have in there. All of these things, all of these features are possible via the primitives that I talked about on segments in the previous slides. So you do ordering because the segment store appends only at the end of the segment. So, and the order in which it receives the writes is the order in which it's going to present them to the readers. We have consistency, and now I'm going to talk about elasticity in a little bit. And yes, strings are lightweight as a file. We can create as many as you want them because they are, in essence, they have very little metadata overhead. So a string is made of one or more segments. So if you see in the graph below, when you get some data coming in, it may be routed to one or more segments which are part of the stream. Now, how do we route that data to the segment? When you send an event, you can provide an optional routing key. That's something that that you as a user know how to generate. If you do not provide it, we're gonna go and randomly choose a segment for you to write to. The reason why we have routing keys is to preserve write order. So this last bullet is one of the most important things that you need to remember. The write order of events is preserved by routing key. So across routing keys, we do not guarantee ordering, but for any given routing key and writer that comes from a single writer, that's how we ensure order. If you have multiple writers, even though they may have the same routing keys, we do not guarantee ordering. And even within the same router, if you have different routing keys, we do not guarantee order. The only thing that we guarantee order from is if you use the same routing key from the same event stream writer. All right, let's talk a little bit about elasticity. All right, so how does elasticity work? So first of all, we seal a segment, and then all we have to do is replace the original segment with two new ones. The Pravega controller is the one who's doing that. So based on the metrics that are stored in a particular segment in its attributes, the various signals are sent to the controller and based on some configuration that you define when you create the stream, it knows, okay, now one segment is getting too hot, it's getting too much data, so it's time to break it down into two segments. The reason we want to do this is because, like I said in the beginning, a segment can only be processed by a single physical host at any given time. So there's only so much CPU, so much memory, and so many resources available on that machine. But if you take the traffic that is assigned to this segment and you break it down into two segments, and you are free to use two different hosts. So now you have double the capacity for it. So the controller is the one that continuously monitors the segments to see if they're getting too hot. And in that case, what it's going to do is going to go and perform what we call scaling or elasticity in standard terms. That is done by we create two new segments, we seal the first one, and then the writers, when they see that they can no longer append to that original segment, they're going to go query the controller. The controller is going to say, okay, this segment has been replaced by these two other ones, so you go figure out which one you want to write to. Yes, and that's the thing I just said. So the segments may be distributed throughout the cluster to balance the load. Let's give an example. So you have your routing keys. The routing keys in our client are strings. What we do is we hash them to a uniform space, let's say from 0 to 1, for example. And then the segments within a stream are mapped to that routing space. So at any given time, the routing space is continuously, it's always covered up by a set of segments. No two segments may overlap in routing key space, and and each segment has a continuous range within the routing key space. So in this case, between up until time t0, we have one segment, and that segment got split into two of them, and you see how the successor of the original segment occupy the whole routing key space. At time t1, the segment on top, which is this guy, got split again, and you see now we have three segments, and they all occupy the whole routing key space. Well, what happened at time t2? At time t2, the controller realized, hey, those segments at the top, well, they're not getting enough traffic, so maybe instead of them using resources or whatever they do, maybe it's okay to combine them into a single segment and just assign that segment to a single host, so we can actually free up some resources. And that's called a merge. The merge is essentially the opposite of a split. We take two segments which are adjacent in a routing key space, and we replace them with a single segment. All right, let's work through an actual example. So let's assume that we have this thing. We have the time at the bottom, and we have the routing key space as the vertical axis. And we have a stream. Initially, we start the stream with one segment. That segment occupies the entire routing key space. So all the events from all the routers will end up in going to this segment. At time t1, the controller says, okay, there is too much data coming into this segment. Let's go and make a split. So it replaces segment 0 with two segments, 1 and 2, and they will equally divide the routing key space. So segment 1 takes 0.5 to 1.0, and segment 2 gets 0 to 0.5. So any event with routing keys that hash to the upper portion of the routing key space will end up having their events written to segment 1. Any events with the routing keys that hash to the bottom portion of the key space will end up going to segment 2. Now, at time t2, segment 2 is becoming too hot, and the controller says, okay, we're going to go and break segment 2 into 3 and 4. And you can see that segment 1 is not touched. It still has its own, the same routing key space, which is half of the entire space, while segments 3 and 4 end up equally dividing the bottom part. So 3 and 4 get each about a quarter of the routing key space, while segment 1 gets about half. At time t3, segment 1 becomes hot, and the controller is going to break it down into like 2 more. At this point, we have 4 segments, and all of them happen to use a equal share of the routing key space. Okay, and finally, in my example, the controller realized that segment 6 and segment 3 are not getting enough traffic, so it decides to merge them into segment 7. So this is how we get from 1 segment to 2 to 3 to 4 and back to 3, based on some hypothetical example. So you may wonder, okay, given this distribution of segment, how is it that we ensure ordering within the same routing key? So let's take, for example, all events with routing key 0.4. Let's do 0.4. And 0.4 is somewhere here between 0.25 and 0.5. So it'll be somewhere over here. So when the writer writes events with 0.4, they're going to end up in segment 0. So it's going to be event 1, 2, 3, 4, 5, 6, 7. All right. Well, since we append those events to segment 0, when we read them back, we're going to read them in the same order, because we're going to start reading from the beginning of the segment, and we're going to go all the way to the end. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7. Okay. When we get this at T1, we know for routing key 0.4, the successor is going to be segment 2. So we are not going to read from segment 2 until we have finished reading from segment 0. So even though there may be events with different routing keys in segment 0 and in segment 2, within the same routing key, the events will be in order. Even though while you are reading from those segments, you may get events with different routing keys. For the same routing keys, your events will be in the same order in which they were generated. And we can extend the same example with the next few slides. So with the next few segments. So the same is going to happen with segment 3. 3 is not going to be read until segment 2 has been fully read. And similarly, segment 7 is not going to be fully read. Sorry, we're not going to read from segment 7 until we have read from segment 3 and segment 6, which means that segment 0, 1, 2, 3, and 6 have to be fully read before we even start reading segment 7. So when you, if you write your applications and you see, you are surprised by how various events from different routing keys are being served to you via the readers, you should consider that this is how a Pravega reader works. All right, the next topic I want to touch upon is transactions. So transactions enable us to automatically commit a set of maybe related events. So while with a single event writer, if you have multiple events, you can only send one event at a time. But then if, let's say your producer crashes or just decides it, oh man, I shouldn't have done that, there is no way to take whatever event you have written and take it back and say, okay, well, I don't want to do this anymore. The solution for that, which exists in many other data storage systems for a long time, is called transactions. A transaction enables you to stream many events into a transaction, and there is absolutely no size limit. It doesn't matter how many segments this transaction spans, because transaction is a distributed concept. And then when you are ready, when you say, okay, I have accumulated everything I want in this transaction, and they say, okay, you have two choices. You can abort it. If you abort everything you have done, it's going to be deleted and discarded. But until you issue a commit, the events that you have written in that transaction will not be visible to the readers, nor will they affect the reading process. That's because underneath, when we create transactions, what we do is we create separate segments. For each of the segments involved, we accumulate the data in there, but those segments are not actually part of the stream, so they're not actually visible to the readers until you hit commit. So when you do commit, we will commit every single segment of that transaction. We're going to merge it into their parent segments, and that's when the data becomes available for reading. So what we guarantee is that all the events within your transactions will go into the stream. So it's either going to be all or nothing. The transaction will be contiguous for any given routing keys. However, just like we have it for event stream writers, we do not guarantee order across routing keys. And a read following a commit may not immediately receive the event. That's because when you do a commit on the transaction, what we do is we send a message to the controller. The controller has a durable queue. It just puts the commit for processing, and the controller will eventually process that thing. Usually, it takes a few milliseconds for that to happen, but if there's a large volume of transactions to process, they will be serialized. So it may take a few seconds for everything to happen. So that's one thing. So what we guarantee is that the transaction will eventually be committed, but it's not going to be dropped on the floor. It's going to be there. So let's work through a little example. Suppose in this case, we have a writer on the left, we have our controller, which is one of the components of Pravega, and on the right, we have segments which are part of a stream. All right. So the writer says, okay, I want to create a transaction. It goes to the controller makes a record of that transaction and says, okay, it's open. Now, the writer is going to go and append various events to those transaction segments. It makes maybe in this example, it makes appends 6 events to 3 segments. Okay, now the writer says, okay, commit this thing. The controller commits them, and what it does, it merges the transaction segments into their parent segments. And after that thing is done, which is in the background, the transaction has been committed, and now is when your events are actually visible for reading. So how do you use transactions? And these are just some high-level pointers, and there's a lot more documentation on our website for this. To create one, use your event stream client factory, and there's an API called create transactional event writer. This will get you an object called transaction event stream writer. And on this guy, you invoke something called begin transaction. This will give you a transaction object. The transaction object has a field, a getter called get ID. So it's important for you as a producer to remember the ID, because in case your process crashes, the only way to get a previously created transaction and continue working on it is by passing that ID to an API called get transaction. When you are ready to commit a transaction, simply invoke commit, and just remember that it may take a while for readers to see the transaction event. If you want to abort the transaction, there's an API called abort. Just invoke that one, and your data will be cleaned up right away. Otherwise, if you don't invoke abort, your data will still be present on the cluster for some amount of time. We do clean up things, but if you make a lot of transactions, and if you don't abort them, and you have a very small LTS backend, then you may run out of space. So be diligent, and please invoke abort on the transactions if you plan to get rid of them. Yes, I'm sorry, that's what I meant. So to abort it, you just invoke abort. All right, getting towards the more interesting stuff. So Tom will talk about the state synchronizer in more detail tomorrow, and what I'm doing now is just a high-level introduction to this thing. So the state synchronizer is an alternative to distributed state synchronization using Pravega. So you may remember that. So you may know that, okay, in order to do distributed synchronization, you use something like Zookeeper or Raft. Okay, well, you can use Zookeeper or Raft or your favorite distributed synchronization primitive. But if you don't want to go deal with yet another Zookeeper installation or some other operational headaches, we provide you a primitive which you can use. So the way this thing works is on each of the objects that you want to synchronize, you have a local in-memory data structure. It doesn't really matter what this thing is, as long as you provide some way to retrieve deltas and serialize your changes. So in my example, it's going to be more or less a hash map, a collection of key value pairs, which is stored in a hash map. So well, each delta in such a hash map could be an insert, a removal, an update. Well, that's pretty much everything you can do. So what happens is every time you create a state synchronizer, in the backend, it creates a segment. And if you remember what I said in the beginning of this presentation, segments have appends, but they also have offset conditional appends. And this is what I mean here by compare and set server side. So we have our initial data in our hash map. Then we want to make an update, say I want to insert a new value. Then I make a second update, I insert value 2, and then at the end, every now and then, the state synchronizer is going to go and compact this data. Why? Because if you have a segment where you only record the updates, well, that's going to eventually, if you do a lot of these updates, that's going to be a very, very big segment. So the state synchronizer is going to take care of compaction for you to make sure that your segment is actually in its smallest state ever, so it doesn't occupy too much space. So let's see with a different example how this works. So we have a Pravega segment, which is your backend storage. Every time you make an update, you write to the log. And when you make an offset conditional append, let's say this. So you have the first thing. You have your segment, you say, okay, I have inserted something. Update uses, I inserted the key A that maps to value 1. Then The second one, so you see we have two state synchronizers. Sorry, we have two clients of the state synchronizer. In the first one, the one on the top made an update. So the second guy says, okay, I'm gonna make a second update and I'm gonna condition on the offset being 2. So I'm gonna make update U prime. So that works because the current length of the segment was 2. However, a third attempt, okay, I want to make update U second, but I'm going to condition it on the offset being 2. Well, at this point, the next update is not 2, it's actually 3. So the update is going to be rejected. So in this case, the state synchronizer running on that client is going to go, okay, at this point, I'm going to go and read the latest state from the segment, and I'm going to go update my memory state. So what this thing, the key takeaway from here is that state changes are not immediately propagated to clients, but they will be propagated if you try to make a change and you are not able to prove that you have the latest value, the latest state from the server. The way you prove that is by doing a conditional update. You as a user, you do not have to do this ever because this is all abstracted for you. But the state synchronizer does this for you. I strongly encourage you to go read the documentation on Pravega.io about the state synchronizer because that has a lot more information than what I can present in a few slides over here. And it has a lot more examples and how to use it and how not to use it. So what do we use state synchronizer for? Let me start with actually from the bottom up. In Pravega, we use it for reader group coordination. So when you have readers from a stream, you may have multiple readers, but those readers have to coordinate between them to know, okay, which segments should I be reading from? We want to make sure that no two readers read from the same segment at the same time, and that no segments are being left behind. And in order for this to happen, they have to synchronize their state, and each reader group has one of those state synchronizers, has one of those segments I showed before. And when readers have to go and be reshuffled around and be assigned to new segments, they go and update the state in that state synchronizer, which is then propagated to every other reader. And that's why everybody knows what everybody else is doing. And what you could use this for other use cases is, okay, pretty much if anything yet you can probably use Zookeeper for, you can probably use this for. So you can use coordination for microservices. You can do a replicate state machine. You can do leader election with this thing. And we have an example of how to do that. You can do host membership. You can manage transactions. And you can even, if you want, you can go and store schema or configuration in it. You can do it, but there's other ways of doing it too. So this is not the only way of doing it. Okay, that's why I have a link here. And this is also accessible if you just type in Pravega.io and follow the documentation. You're going to find this here too. So please go and read this documentation because it has a lot more details and examples than what I can present here. Okay, last thing I want to talk about is one of the things that we are currently working on, and that's why this is marked as beta. So besides streams, we want to offer another complement, another primitive to users to store arbitrary data and be able to retrieve it right away. And we call this key value tables. So what you may not know is that this is also how we store all of the data that we have internally. At the very base of key value tables, we have something called table segments. So table segments are nothing, are pretty much a layer on top of the same segments, same type of segments that we use for streams, when we have additional data structures to organize the data. So they are key value stores on top of regular Pravega segments. Anytime you make an update, like I want to insert, I want to update, I want to remove a key value pair, we append those to the segment. So we treat the main segment as a changelog. Now, what we do is we hash the keys to 16 bytes, and those hashes are stored in segment attributes. Well, remember when I told you that with 16-byte attribute IDs and 8-byte values, you can do a lot? Yeah, well, yes, you can even implement a key value store. We use this to maintain any metadata that we have in Pravega. So I try to think of everything we have in there. So everything you have, scopes, streams, segments within the streams, internal transactions, tier 2 LTS chunk metadata. So segments in tier 2 are broken down into chunks. The metadata for those chunks are stored in our internal table segments. Schema registry, and I'm pretty sure there's a few more. So all of our metadata is stored in table segments. So it's stored within the stuff that we maintain. We do not store any metadata within Zookeeper. We only use Zookeeper internally to do basic coordination between the controller and segment storage, so we know what each of them is doing. But that's pretty much it. We do not store any metadata outside of Pravega. Now, a couple of releases ago in 0.8, which was last year, we decided, okay, let's take these table segments and let's go and try to expose them to the outside and make another primitive, which is a complement to our streams. So that's where key value tables came from. Key value tables are nothing more but a distributed key value store, which are backed by table segments. What you can do with these guys, you can do single key insertions, updates, or removals. Well, of course, otherwise you will not have a key value table. You can also do conditional. You can also do them either conditional or unconditional. So every time you make an update, you get something called a version, which is the same as an E tag, if you've heard of that term. So if you care, you can take that E tag and provide it back to another update and say, okay, only update this key if this version matches whatever is on the server. So that's what a conditional update is. Also, you can do multi-key atomic inserts, updates, or removals. So if you don't want to go and update a single key at once, sorry, if you have multiple keys, if you have 4 keys, and you want to make sure that these updates only go in all at once or none at all, then we allow you to do that. There's a few caveats to that, and they are well documented within the API. And within those updates, you can go and you can mix and match conditional or unconditional. So say, I have four keys I want to update, but only one of them has to match a condition while the other guys can do whatever. And you can do that. You can retrieve one key or multiple keys at any given time, and you can iterate through all the keys or entries. And right now with the current API, keys can be grouped into key families. That's optional. But one thing to know is that multi-key operations and iterators right now, they only work on keys within the same key family. So how do you use this thing? Okay, so to create a key value table, in the Pravega client, there's something called a key value table manager. You create a key value table. Just like you create a stream, this is the system implementation for that. To access it, you get the key value table factory and you have the API called for key value table. That gives you a key value table implementation. Then you use the key value table for all the operation that you want on the key value table. So you can do all of your insertions, updates, removals, retrievals, all these things. So it has a very rich API, and there's a very thick Java doc which accompanies each of them. Okay, I need to stress this out very, very clearly. So this API is beta, it's marked as beta, and we do know that in version 0.10, which is coming sometime in the summer, we are going to change the API. So if you do want to use this for the hackathon, please make sure that you code against the whatever APIs we have published in 0.9, which is the current ones. So that's the only thing which I want to know. I want to share with you. All right, so that's pretty much everything I want to talk about now, and we can spend the next 5 to 10 minutes. If you guys have questions, feel free to shoot them in the chat. And if we have overspill, I'm going to be in the mentor session, which comes just after this, so we can continue the conversation there. So, Asta, how are we going to do the Q&A for this?
Sure. First of all, thank you so much, Andrei, for this session. It was really, really insightful and helpful. Let me quickly check the chat if there are any questions which have been asked. So I think for all of those who are out there between the meeting as well as the YouTube live that we are running, if there are any questions, please do post on the channel. I think Ace has a comment here. Ace, would you like to unmute yourself and kind of, you know, check in with Andrei on the comment?
No, but I just want to say thank you, Andrei, for taking the time to present today. I had some interest in applying this to a blockchain style transaction for music streaming, but I'm gonna build that out with somebody. I know there's some components that are not quite don't quite gel, but I'm very interested in seeing how that works out. But thank you, Andrei.
Sure, you're welcome.
Thanks a lot. In case we don't have any more questions, we would, so if we have any other questions on Zoom, what we will do, YouTube, what we'll do is we'll quickly get those posted on Slack so that Andrei, you could answer those on Slack. And I think we have Andrei in the next mentor session as well. So if you have any more questions, we can definitely take it up there. But this was really, really insightful. Thank you so much, Andrei, for doing this. And you know, thank you all the participants for joining in.
There's a question. So,
oh, sorry, yeah.
Does the current Pravega Docker image support key value tables? So the current Pravega Docker image version 0.9, and yes, we have key value tables, but they are, like I said, they are beta. So you can code against that, and feel free to use it. Yes, it does. Yes, so feel free to ask questions on the Slack. I'll answer it. Anybody else can answer it. And if you want to see this presentation again, I can upload this on the Slack channel. Asta, where should I put in the mentors? Where should I put this? Announcements? If not, I'm just going to choose one.
Andrei, you can post it on the mentors channel. Harish here from AngelLac.
Okay, I'll do it after I'm done here.
Hi everyone, Trisha from AngelHack here. I think if you guys have no more questions, we'll end the session today. And then please join us for the mentor office hours that we'll be hosting in a bit.
All right. Well, then thanks for listening to me, guys. And I'll see you in like 10 minutes, 7 minutes. And happy coding.
Thank you, Andrei. See you guys, everyone.